Hello, and welcome to Introduction to Temperature video. This is video 7.1a for physics. When we get started with these videos, it's important to remember that you can pause at any time and take notes and go back over and come back to them again later if you need to. So let's start with kinetic theory ideas. Really, the idea of kinetic theory began in ancient times with a scientist by the name of Democritus. Democritus named the smallest piece of matter an atom. He's the one that really decided that the things that we look at are made up of smaller objects, and those smaller objects are atoms. This got people thinking about, well, what are atoms and how do they interact and things like that? Well, at the time, Democritus felt that atoms were solid and they were it. There was nothing else in them. We now know that that, of course, is not true. And inside the atom, we have subatomic particles, which are the nuclei in the nuclei and as electrons revolving around that or orbiting around that. So now we don't have to just talk about an atom. We can actually also talk about atomic mass, and or molecular mass. And when we're talking about atomic mass or molecular mass, we're talking about the relative mass of an individual atom or the relative mass of molecules. By relative mass, what I mean is that relative mass is based around what the mass of a carbon-12 atom is. Carbon-12 was arbitrarily chosen as being our standard. So when we talk about carbon-12, we say that its atomic mass is equal to 12.0000 U's meaning the symbol for atomic mass. Hydrogen 1, based on that, means that hydrogen has an atomic mass of 1.0079 U's. Again, hydrogen's mass is based on carbon's mass. Carbon's mass was arbitrarily set. Because of this, we have to somehow have a relationship between a U and a kilogram. And one atomic mass unit is equal to 1.6605 times 10 to the negative 27 kilograms. So super, super tiny, which is one reason why the atomic mass unit was developed, because the mass of atoms is so small. So it's sort of like an extreme of our unit prefixes. And at this point, when we talk about atomic mass and molecular mass, the reason that it's important is because we have to understand that in order to see enough carbon or enough hydrogen for us to recognize that it's there, whether it be in the form of coal or in a gas sample or something else, we have to have lots and lots of each atom. So we have to know how many atoms we have as well as how big they are. This gets us to a whole list of these relative atomic masses. You will find the rest of the atomic mass list on the periodic table that's in the back of the book. So when we are talking about different things in this course, especially in this particular section where we're dealing with heating things up and cooling things down, we have to remember that if we are discussing an element, then we typically have a sample of an element, like a sample of gold, a bar of gold. But really, when we look at it, the smallest portion of an element we can have is an atom. However, if we're talking about getting down to molecular mass, we're no longer talking about just an atom. We are talking about the smallest unit of a compound. We're not going to get into lots of detail about this right now, but these are some of the words and ideas that you're going to have to keep in mind in this section, and we'll come back to them in more detail in class itself when we get to solving some problems about it. But the kinetic theory is started with Democritus with what an atom is, and then now it continues on and is based on the fact that we have atoms and molecules, and that there's a theory about how they all move around. This is currently best described by what we call Brownian motion. Brownian motion is basically the idea that atoms are constantly moving randomly. And of course, they move differently depending on what state they're in. So if they are a solid, they're pretty firmly held together with the bonds between their adjacent molecules and themselves. However, they still vibrate back and forth, or up and down, or both, but they always remain that close bond. If they are in liquid form, their Brownian motion is much more chaotic because the molecules can slide past each other. They're still bonded together, but they're loosely bonded so they can slide past each other. And then, of course, we get to the gas. And gases molecules are no longer really bonded to each other much at all, and they can go flying all over the place and fill as much space as possible. Their particular types of motion is dependent on their temperature. Because remember, as you have a substance, let's say that we are talking about water. If we have water at a cold temperature, it's a solid as ice. We increase the temperature and it becomes liquid water. We increase the temperature again and it becomes water vapor. Each of those times, the molecules get moving faster because temperature essentially is giving each molecule more energy. So when we're talking about Brownian motion and temperature, Brownian motion is the constant movement of atoms. It is chaotic, and it increases as we increase the temperature, because temperature, while we typically think of it as being how hot or cold a substance is, really temperature is the average kinetic energy of the molecules. So it is telling us kinetic energy is the energy of motion, so it's basically telling us how much motion the particles have. And in knowing that, we can then know the temperature, and of course, if we want to know the temperature, we need to understand thermometers and how thermometers work. So when we are measuring temperature, we typically use a thermometer in everyday life here in the US. Of course, we use a thermometer that has scales of degrees Fahrenheit. In science, we don't use those. Instead, we convert to degrees Celsius. And to make the conversion between Fahrenheit and degrees Celsius, we have to do a little equation here. So if you want your temperature in degrees Celsius, but you have it in Fahrenheit, you have to take 5/9 of your temperature in degrees Fahrenheit after you've subtracted 32. So why? Why is that 32 there, and why is it 5/9? Well, number one is because both Celsius and Fahrenheit are arbitrary scales. Celsius starts with freezing being at 0 degrees Celsius and freezing of water at 0 degrees Celsius and boiling of water at 100 degrees Celsius. So the range of what we typically deal with is from 0 degrees to 100 degrees Celsius. Fahrenheit, for that same range from the freezing of water to the boiling of water, is from 32 degrees Celsius, from 32 degrees Fahrenheit to 212 degrees Fahrenheit. So when they were coming up with the Fahrenheit scale, they didn't base it around water, even though since it's so prevalent, they probably should have. So 1 degree change in Fahrenheit does not equal 1 degree change in Celsius. And then when we really got into it and we decided that, you know what, water is not really the best thing to be looking at here because there's so many other things that can get significantly colder than water that we deal with, they then came up with another temperature scale called Kelvin. The Kelvin temperature scale is our absolute temperature scale because water freezes at 273 Kelvin, approximately, and it boils at approximately 373 Kelvin. Notice that there's no degree sign in there, degree symbol, because they've determined that since Kelvin is our absolute scale, it doesn't need to have the degree symbol with it. It is like any other unit, which means that 0 Kelvin is when there is no other temperature. You cannot get colder. It is absolute 0. At that point in time, if the temperature is a measure of the average kinetic energy of molecules, at 0 Kelvin, we must be at absolute 0, absolute no kinetic energy, which means that all of the molecules must not be moving any longer, which is a pretty far out there limit to what's going on. And at this point in time, we have not yet gotten anything to go all the way down to 0 Kelvin. So it'll be interesting to see if we can get there. So if we know that we can change temperature of things, and we know we can do that because we have thermometers and we can heat things up with fire, we can cool things down by putting them in the refrigerator, things like that. A thermometer works because the liquid inside it, which is typically some sort of an alcohol liquid, is increasing or decreasing its height or the length of the column depending on what the temperature changes. This works because most substances expand when they get hot and contract when they get cool. There's an exception that we'll talk about in a little bit, but basically that's how our thermometers work. So let's talk about what is going on when we have, say, something hot that we put with something cold. The 0th law of thermodynamics. I'm going to tell you what this law is first, and then we're going to talk about it in a couple of examples to see what is going on here, really. If the 0th law of thermodynamics says, if 2 systems are in thermal equilibrium with a 3rd system, then they are in thermal equilibrium with each other. So again, if 2 systems are in thermal equilibrium with a 3rd system, then they are in thermal equilibrium with each other. What that means is thermal equilibrium means that 2 or more systems are at the same temperature. Thermal equilibrium means at the same temperature. And so scientifically what this means is that there is no net thermal energy exchanged. Which means there could be thermal energy going back and forth between the 2 objects because they're touching each other, or between the 2 systems because they're in contact with each other, but there's no net. So as much energy as goes from object A to object B, that same amount of energy goes back from object B to object A, just continually, probably. So the 0th law of thermodynamics says basically that if you have 2 substances that come in contact with each other that are different temperatures, eventually those temperatures will even out. The thermal energy in one will make it to the thermal energy to the other one, make it into the other one as thermal energy. Eventually they will become at the same temperature. If you have a 3rd system where this is also occurring in, then they too will be at thermal equilibrium with the others. Best example of this is in your room, or in a room at, say you go to the library. And you walk into the library and it's super hot outside, so you're hot, but the air conditioning is on in the library, so it feels cool. You then sit down on a chair in the library and it feels really cold to your bottom, to your arms, whatever. Even though the chair feels significantly colder than the rest of the room, because it's been in the room for a long time, the chair and the library are at thermal equilibrium. Which means that after you've been sitting there for a while, and the chair no longer feels cold, you have become in thermal equilibrium with the chair, which means that you have become thermally equalized to the library, to the environment around you. This is an important law of thermodynamics. However, it is called the 0th law as opposed to the 1st law, because it was after they discovered the 1st and 2nd law of thermodynamics that they thought, oh, wait a minute, we really do need to actually state this pretty obvious point as a law. So they called it the 0th law. With this short little video, this should give you some refreshers on temperature and give you an understanding about the temperature scales we're going to be using and why. Bye for now.